Good morning / afternoon, depending upon when you're watching this. We are going to finish our notes that we started taking on Tuesday. So we talked about the goal to show a polynomial function that can be used to approximate for another function. We've got our function f of x, and what we did is we created the polynomial function p of x, which is our tangent line. We all know how to find the tangent line. We use our point slope form, and we use the derivative of the function. They share this point in common, and we can also say that p of c would also have to equal f prime of c. So our polynomial is being given with respect to c. So this is a polynomial which is expanded. This is the terminology that we use about c. Another way to say that is the polynomial is centered at c. And we use that to talk about where we're having that shared common point that we're going to start with. So Taylor and Maclaurin series are very similar, and the polynomials are very similar. However, it just depends on where they're centered at. And we can move this and rotate it around and change where our c value is, but it's still going to be the same technique and still the same idea. So here's the example that we did, finding the tangent line to y equals e of x, and using that tangent line to approximate a value of a function. So here's our function y equals e of x, here's our tangent line, and we found a value, and we're able to approximate that f of 0.1 is 1.1. And we did that again, centering it at x equals 1. So it's changing our value because we're changing where we are along the function, y equals e to the x. We can make this a little bit better, and that's our goal. How can we make this approximation better? We've got our function. We've got y equals e to the x power. And we had our linear equation, which was 1x plus 1. There's that shared point that they have in common at 0. And when we zoom in, we can see that it's pretty close to the function for a certain period of time. As we get further and further away from where we're centered, it's not a very good representation or a good example or approximation for the function. So what we're trying to do with these two different polynomials, both Taylor and Maclaurin's, is to make them better. We want to be able to write better and better polynomials to represent the function. So what we would do is add a second initial condition. So if we have our first one, our y equals e to the x, and we've got the graph of that, our y2 is our first tangent, and that's pretty good at x equals 0, but it's not good as we go further and further away. So make another initial condition. Well, if we do y double prime of x, that's still going to be e to the x. And if we take that at 0, we get 1. So we've got this new part to go in. So we've got another polynomial function that we can write, which we're going to plug in for y3. And we're going to say that's 1 plus x plus half x squared. Well, let's put that in. As our calculator Tokyo drifts over there. So we've got 1 plus x plus 0.5 x squared. And as we can see by looking at that, it's a better approximation from now here to about here. And we still have the same problem as we go further and further away. It's going to be further and further from our actual function. But it's following the curve pretty well in this region. we can make it better. And if we keep expanding it and using initial conditions and adding to this, we're going to get better and better representations of that function in the region. And that's our goal with using these two polynomials. So here is the polynomial that you guys had to write down in class, and it's used to approximate what we call transcendental, non-algebraic functions, so sines, cosines, using your trig functions, the logarithmic functions. And for Maclaurin's, we are centering it when x equals 0. So we're going to use this and use those tangent line approximations to create our formula. F evaluated at 0 times x to the 0th, we know that's 1 times whatever our coefficient is here, plus f prime of 0 times x to the first, plus f double prime of 0 times x squared over, this is in fact 2 factorial. The general term pattern is f to the nth derivative of 0, because that's where we're centering it, over n factorial times x to the nth power. And if we would do this for the problem we just had, we would build a better and better function or polynomial that goes close to the curve at that point. So we're going to take a look at that example. We had the first parts of it already built, but let's go over how we do that. We need f of 0, so e to the 0th, 1. We need to find our first derivative, and we want to evaluate our first derivative at 0. We need to find our second derivative and evaluate that at 0. And we can keep building our function by keep taking derivatives and evaluating those derivatives at 0, because that's where we're centering it. And we can build our function based off that. So our polynomial with n terms is going to be f of 0 times x to the 0th power, which is 1, plus f prime of 0 times x to the first, plus f double prime of 0 over 2 factorial x squared, plus f triple prime of 0 over 3 factorial x cubed. And we can keep doing this, and we'll write the general term, which is f, the nth derivative of f of 0 over n factorial times x to the nth power. So down here, this is very typical of what you're going to see. It's asking us to use n equals 4. So this is a 4th degree Taylor, or Maclaurin polynomial. This is our degree because n is our exponent up here. So we're going to keep expanding this up until n equals 4. And then we're going to use that to evaluate f of 0.1. So we've got p sub 4 of x, 1 plus x plus 1 over 2 factorial x squared, plus 1 over 3 factorial x cubed, plus 1 over 4 factorial x to the 4th. So we've got our polynomial, and we need to approximate when f of 0.1. So we're going to take f of 0.1 and plug it in for x. And then what we're going to do is grab our calculator, plug that in, and evaluate it. You can use your factorial key, or you can actually figure it out since those are pretty small numbers. So 2 factorial is 2 times 1, 3 factorial, 3 times 2 times 1, so on and so forth. So we're going to compare this to the actual. We want to compare it. Here's our original function. We want to compare this to the actual. So e to the 0.1. There we go. There's the comparison between the two. We've got our approximation we've got our approximation of 1.1051708 to the actual 1.1051709. That's pretty darn close. And if we take a look at this on our calculator, here's our P sub 4, our fourth degree Maclaurin polynomial, and if we graph it, that's pretty close to our actual function for a while in that region. So that's a pretty good representation for a certain value along the function. And we're going to look at that later. But this is the basic idea. So Taylor is a little bit different, but just slightly. And all we're doing with Taylor is changing where our function is centered, or our polynomial. So instead of having it centered at x equals 0, we're going to center it somewhere this direction or the other direction, and centering it there. So this is our function, and this is how we build it. So I suggest you pause here and write it down. Instead of evaluating our derivatives at 0, we're doing it in terms of c, and this is x minus c, because previously it was x minus 0, so we didn't need to include that quantity, just the x. So we're going to take a look at one when it's centered at 0, or at 1. So what we're going to find is the derivatives of these for a little bit, and then we're going to build our polynomial from there. So to start us off, here's our function. Here are the first 4 derivatives, and here are the function and those derivatives evaluated at 1, since we're centering it at 1. That's what we're going to plug in for x each time. So we've got our general form for a Taylor polynomial right here. They are factorials on the bottom. This is really over 1 factorial. So we don't have to worry about this. This is 0 factorial is 1, so it still works there. And here's our general form for ln of x. So here's our Taylor polynomial for ln of x. And what we're going to do is we are going to do a 4th degree Taylor polynomial and approximate it for f of 0.9. And we're going to see how close we can get. So here's the 4th degree Taylor polynomial for this example. It's written out, and then we are plugging in 0.9. So when we plug 0.9, we can simplify each of these fractions and plug that into our calculator. We get approximately negative 0.105, I believe I wrote 358. And let's compare that to the actual. So if we're taking the natural log of 0.9, when we plug that into our calculator, we get negative 0.1053605. That's pretty close. So these are excellent ways to approximate different values which are close to where we're centering the functions. And we're going to take a little look at those a little bit later. Just remember, these are for a finite series. We're going to look at taking these series to infinity, but the polynomials are for a finite set of groups. So take a look at this homework, see if you can knock some of these out, and make sure you're ready to go to turn in homework on the block day. Have a good day.